Great. So we're going to start from the point that we stopped this morning, like this. It was just like we generated the waveforms, the plus and the cross waveform with some parameters that we gave to this function here that is get time domain waveform. And let's just run this cell. Another thing is, oops, I didn't define the noises. So yeah, this can happen. So okay, let's define what are the noises. So yeah, you see here, I don't need to define the path. Just need to run the cell again. Okay, so we generate the waveform on here, and we can check as well. For some of you, do you prefer the slides or do you prefer to run the notebook as it is, like this? Can you guys vote? Can you guys like? Okay, I'll keep this as experimental. If you want to change to the slides, we can change. But I think that this way, or it's too small to read. I think maybe. Yeah, but
no, it's okay, Philippe. I can read it perfectly. It's okay.
Okay.
Yeah.
But I think for people here, it's kind of like a challenger to like see like.
Yeah, sure. Yes.
Yeah. We'll filter people who has like very good sight. I think that Antonio is already out of this. I mean. Okay.
Okay, whatever you like, Philippe. I mean, it's.
I mean, let's continue with this because it's kind of like a nicer to see. So let's do this. One. Yes. Yes.
What about PyCBC? Are we going to install it here? Was it supposed first?
Yeah, in the first lecture, I said like as an exercise to install using Anaconda, create a new environment. Yeah, I think your problem is because you are not on the environment that was supposed to be. Because I think that as I saw your notebook, your Jupyter Lab is in the FastAI environment. Change it to the. I think that you told me yesterday that you create a new environment, as I said, with the gravitational wave stuff. Change it to this and try to run again. Okay. And try to. If not, I mean, I'll go after this and we can fix it. But yes, in the first lecture, I have like the installation guide for the PyCBC. I even recommend like to install first PyCBC, and later GWPy. And also it has like the how to install the GWPy and PyCBC in the Google Colab as well. Also nice. But I can always tell again, you guys just tell me. Yes, one thing that I like to keep tracking is the sizes of the vectors, like because this HP, this polarization cross, I can show to you right now here. It says this object is a time series of this, and I can even like type values. Let me go. See, it has classes. So if you type like the polarization like this vector like this, and you type dot data, you see it gives us an array with these values like this, which are like the time series by itself. But still, we are still preparing everything. And sometimes I like to check these dimensions, like the shape, like because this has like the length of the polarization vector of the array that we are dealing, and to compare with the noise like this. And you see that the noise is quite big. I mean, look at this. So we have to find a way to reduce the size of my noise, because I have like this long string of noise, to later take this size of noise, which has the same size of my waveform, to inject the noise in my waveform, to make the waveform be a little bit more closer to what we are going to see on the detector, right? We are going to check this in a few moments, but let's first see what we have on this polarization, what we have on this time series, and we can pass the same kind of argument as we did with the LIGO signals as well. The same notch, band pass, and everything. But before we do this, because this is dealt by GWPy, and as we saw here, this is a time series. You see some. This is a PyCBC type, okay? Because you're dealing with two packages, PyCBC and GWPy, you have like to keep in mind that, so, okay, if I'm going to give GWPy this time series, I have to make in a way that GWPy knows what is. Don't ask me why they are different, because they are developed for the same kind of group, but I don't know if the people don't agree with each other or something, or prefer like this. So you always have like to convert from one to another. The good thing is you can always do this with GWPy. It has this function here that's called the from PyCBC. This function takes any time series generated by the PyCBC and convert in a nicer way to the GWPy. It's only like this. So every time when, okay, I generate everything with PyCBC, I generate the things that I need. Now I'm going to work with GWPy. I need to convert. If I have to work back with the PyCBC, PyCBC has a function that is called from GWPy, and you can come back later. You can always do this like back and forth. And most of the time that you give some error, it will be because of this. You are using some type, some data types, or some time series or something that is from one package in another one. So we always have like to keep this in mind, okay? We run this to apply the things with GWPy, the notches and the bandpass, and we can see the waveform, like the signal strength in this way, like this. Notice that like the x value is not in the GPS time coordinate yet. We are going to fix this when we inject the noise, but so far it's just like to check this. It's just like to keep things in check. And you see that this is like a 10 to the minus 23, 22. I think that's, yes, 22. And we have the spiraling phase, and you have like the peak, the merges, and you have the ring down here. So what we are going to do, we are going to generate this Q transform, which is a really useful tool and to visualize the sensitivity of the detectors for signal of the gravitational waves, like this. And yes. Yes.
What's the decrease before the big increase in the before the from the amplitude of the oscillation?
This one?
Yeah, you are increasing, there is a decrease, and then you're passing increase.
I have no idea. Maybe Nico or
Can you comment on the question?
Yeah, the question was what was this physical meaning? It has some physical meaning, and the reason like why it has like some increasing. Oh, is there in fact that I'm removing the low frequencies from the, yeah, it can be. So the question was why you have like this funny things here, this funny artifact and increase and then come back later like this. And Nico said that commenters like it might be related to the removing of the frequencies like the low and the high pass, like the band frequencies.
Oh yeah.
And we can have like this kind of artifacts generated. Yeah. Okay.
Makes total sense, yes.
Yeah. So yes, I mean I have no idea. I'm just like, okay, I'm doing this, and you know. Actually, it is really good like to have some people on the field that's like catching this kind of thing, because for me, I mean, I would never, okay, it's a signal, I'm just this and just passing. I will completely run over this. It's completely over my head on this.
Yeah.
So
You see, Felipe, one of the things that we did in the past was to make a Fourier transform of the signal, and then selecting regions of frequency and making the inverse transform just to see what happens with the signal. And it's very clear, this effect. It's
yeah.
really.
So we are going to generate this Q graphs. I like to say Q graph, but it's we have like to transform. We use like a fast Fourier transform to go from these signal strengths to make the sensitivity plots from the, you have like the time, the frequency, and the power of the noise, like this. And these are really, really nice because we can produce this really beautiful image that we saw before. And we can use this image to classify events, because they also use this Q graph like to classify glitches, to see glitches on the detectors. And if you look for convolutional neural networks and gravitational waves, you see lots of paper using these Q graphs, using this information from this Q graph to classify events and classify glitches or make some trigger detectors or something like this. And we can see from the docs, like from the documentation, this we can transform directly the time series to a Q graph transform like this. And you just need to feed some basic information for the functions, like the frequency range and some transformation range that you have like to sample on this, the kind of normalization and all of these parameters. I mean, we're not going to touch in each one of these. As I said, like it has like lots of tutorials and documentation that explain every detail on this. We are going to use like the most basic ones, like the full ones, which are the usually the ones used by the collaboration. Like we are not going to touch in much things here. But keep in mind that like some of these parameters that we're changing here, it will drastically change the images output that we're going to have. Because what happens is like when you generate these images, you have like this kind of like a very stretched plot like this, because you have like this time signal, and it has usually it has like the dimensions like 500 pixels by 1000 like this. You have like this very wide Q graphs like this, and the machine learning doesn't like these wide images. What the machine learning like, this is more as an artifact from CUDA, from the development of CUDA, because it prefers square matrices like this. It prefers like images with the same height and length like this. You always see like when you saw my yesterday lecture, I put like 224, and it automatically gives the image 224 by 224, 128 by 128, 64 by 64. You always have this kind of filters in machine learning. Why? Because in the development of CUDA and these machine learning libraries, it's far easier for the GPU to treat the matrices operations when the matrices are square. Right? It's far faster, and it works fine. If the matrices are not square, I mean, let's say if the images are not squared like this, it has like this, the width and the length are different and some sort, you can still handle with this, but it will take a little bit more time. So, and this kind of images output, this kind of parameters, you can change this to make this transformation from like a wide images to a more square, and not lose so much information. I mean, it's kind of like it's not clear right now, but we are going to see in a moment why these kind of things matters and why it is important to keep this in mind. Okay, and also like the colors will be set by the normalization scale of the image that we're generating, and some other parameters that you can play as well. Okay. So as Carlos asked this morning, that like sometimes the times that the detector will receive the signal will be different, will be like split. So how we can handle this? How we can like try to match the three detector signals in one in one image like this? And another thing is like we are not going to generate the image from the full signal for the full input. We are more interested when the signal get like more stronger like this in that window that is closer to the merge, okay, very close. So this cell here, it first takes the time, like put the time range for my signal to a time range that we have on the noise. So this is just like to, instead of it have like this, that funny time stamp from minus to 0 and for something, we are changing to the GPS timestamp right now. Okay. This random offset here, this I'm doing this. That's because I have this huge strain of noise. We have like this huge length of noise, and we are randomly selecting a region on this noise. We are like walking over this noise and say, okay, I will select this region for this noise, and this will be my zero time, like this. And from this, we are going to sample the random noise, and we are going to set our signal here. Okay. Here, nothing new. I mean, we are just like convert again in this GWPy series. I'm just like create a new GWPy series, just like to not messing with my original one, so we can have comparison of the same. And here in this cell, we are just like looking for on my signal, where is the time where we get the peak, where the time that the signal is most stronger, like this. Really the time like this here. So what we are doing in that cell, we are scanning all over this time step, and I'll say, oh, here is my peak. Here's the time of my peak. So this function here, like not this function, like this argmax here that we have, this is from NumPy, and it is really nice because you can put like any series, any kind of vector, anything like this, and it is looking for the maximum value of this of the vector or the array that you give, and you return the index where this maximum occurs, like this. So you don't need like to make a fancy algorithm to search about this and this. I think C++ has as well. I think I remember it has this argument vector max. But anyway, so this will return the index. In my case, my index is the timestamp from my signal, which will have the maximum value like this. And here we are setting the window of this time value, like the window like this, in some random width like this. We said like, okay, this is my maximum, and I give like some milliseconds on this window like this. And we are also going to use this same window to apply for my noise. Running this, and we can check what we did so far. And as you can see, we have the noise on this orange, like this. We are take all the same treatments, everything that we did, and we have our signal inside this. But still, we still don't have this our signal with the noise. We're just like only have our pure signal. Like we still need to inject the noise inside. Okay. And another thing that is really important for you and will help you to save some memory is to crop your noise. By crop, I mean because we have like all this huge length of noise, we're just like cropping in the maximum of the time index that we have, 4 seconds after and 4 seconds earlier, like this. Or you can change like 3 seconds, 2 seconds. You can decide wherever that you want to crop. I usually put like this because it's like a reasonable size, and you still get like some lots of information from the noise and from the signal as well. Okay. So we crop this, and we are going now to start to prepare our Q transform. So one of these preparation for the Q transform is this AST, is the amplitude spectral density, which gives us the key indicator of the frequency domain sensitivity of the gravitational wave. Because we are plotting time, frequency, and sensitivity, this amplitude spectral density will give us the value of like the color values, will help us to get the color values like this. And these cells, I mean, I just really like what I did. I copied from a tutorial on the GWPy, and so far I've been using this kind of transformation. Of course, these images are sensitive for this, and we can change the parameters, and we can have like another kind of classification, we can have another kind of data set, anything like this. What I will suggest is just like try to learn using this function, because some of these, it will complain about size of vectors, it will complain about size of windows. You are learning by doing this kind of thing, okay? And I'm not going to explore too much on this, otherwise we are going to lose a lot of time. But I would say like look at the documentation and try to understand what are these kind of bits that are doing this. So far, for our purpose, don't take my word as a gospel, but like, okay, we have to work, we have to keep work. So let's just admit it that these parameters make sense and will not produce any kind of funny thing that you don't expect. And now it's become the important step to not forget to inject the noise that we crop and we treat and everything like this in my signal, okay? If you don't inject this, you will produce like really beautiful image, but they are not real. they don't have like close to the detector. It can be useful for other tests, but not for the one that you are interested, okay? But if you do this, you do not put the noise. Every time that you give the machine in the first epoch, will give you 100% of accuracy. Because you see the noise will have like a very, very ghostly image, and the signal will be like that signal strength thing, like that curve that increases over time. So inject the noise here and apply this whiting, which is another filter that we have like to apply this before the Q transform, that we have to set this. And now we can finally get the Q transform image. It's not the image yet, but yes, we finally get what we want. All of these things here, all of this is just preparation so you can use this. And after you use this, you can plot, okay? And lo and behold, we have some signal here. I don't know. I mean, because the signal, they have like almost the same power of the background. And it's like 20 and 25 black hole masses at 600 megaparsecs. And we have like the random noise on the images. And this here, this like this funny things here, these are the notches that we are imposed. Like this. And you see, it will be like in the, I think that's the frequency, it's like 60 hertz or no, I mean, it's different right now. But it has like the 16 hertz and the 120 hertz as well. It will be feedback. This is the notch on the 60 hertz. I think this is the lowest baseline, and here we have the gravitational wave. we can change. I mean, we can just for fun. Let's just put like a more stronger signal. Let's say instead of 600 megaparsecs, the event was a little bit more closer. So let's run it again. So we have this, nothing new. And you see the signal here is becoming more stronger than the noise, like this. You see like the signal get off the scale. Like this. And this automatically will transmit to the final Q graph. And see, it's just like you can play with this and check as well what kind of a signals that you have, and see you have like very clear like the image that you are already very know from the LIGO collaboration like this. And yes, of course, if you give this to the machine will automatically know that this is a signal, it's not a background. But the previous signal, it will be a little bit much harder for the machine to distinguish, and it will be a little bit more interesting for us as well. Okay, to summarize that we need is just like, okay, we random selected properties of the black holes merged or the compact objects or whatever you want to simulate it. We set distance ranges, we set like based on random selections on random things, and the other interesting parameter we might include as well, like the inclination, like if the signal is coming like directly from us or it's coming like from the other planes or this kind, we can impose some random distribution on this, and the elevation, inclination, everything that we want, like that get waveform parameter. That has, you can make things really crazy there, impose like some random constraints and generate the noises. We want to do this. We want to generate these waveforms, okay? Select a random window from the noise, inject it on my waveform generated, apply whitening, filters, everything that we need to apply, generate this Q graph, and save as an image. We are going to save them as an image using Pillow, which is an image library that is really fast, really good, and very intuitive. But yes, it might become like in the next workshop or next year we do a little bit more in depth of this kind of packages and libraries here. So, since we are also want to include the detector patterns on my signal, yes.
I'm trying to understand what you've done.
Yeah.
So you said that this algorithm understood that there was a signal there. But I missed the part how the algorithm actually learned what our signals.
No. We are going to learn the algorithm in the next lecture. I'm going to, what I'm saying, that's like, if I train the algorithm with images saying that these are the signal, and the other ones, like only the background fluctuation. If I train the algorithm with this kind of image like this way, it will always know what are the signal, because these are completely different images. Let me show you on a very good example. Yeah.
I understand. So you superimpose a signal which you generated synthetically with some noise, right?
Yeah.
And it was the superposition of the two things that you've given as your data.
Yeah.
And then you plotted this.
Yeah, but
stuff, right?
because this signal is so strong, we almost don't see.
Yeah, even the previous one, which was not as strong as compared to the.
Yeah, that.
Still, there was kind of a yellow.
Yes, it was like
right?
some batches, some that,
Right.
which is really good, because sometimes we have some glitches that imitate that kind of a behavior. Sometimes,
Right.
yes.
So, but this seems to be a diagnosis that there was a signal, and I'm just wondering,
Yeah.
I mean, how did this image learn what the signal was? I'm a bit confused about
Yeah,
that.
what the machine learned what the signal was?
Well, because you told us, look, lo and behold, and there's this yellow patch, so there's
Yeah.
your signal. But you didn't, your algorithm was superposition of noise you wait for.
Yeah.
So I didn't understand how the algorithm learned what the signal is.
Oh, the algorithm is not learning,
It
not
didn't
yet.
learn.
No,
So,
no.
so what are you plotting here? So
These are my data images. These are
It's
my
just
data
your
set.
data.
It's just my data. This is just my data. But what I'm trying to try to say that's like, if
you
we,
give the superposition
yes,
of the noise with the,
yes,
with the
exactly.
real waveform.
Exactly.
See that?
exactly. If we feed the algorithm with images only like this way, like very strong image, very strong signal, the machine will automatically learn this kind of a behavior, this kind of thing.
Color map there, I cannot read. What does it say in the
Is
color?
the normalization, normalize the energy. I think that is the squared intensity of the energy.
It's normalized energy.
Yes.
Energy of what?
Because this is like a spectral decomposition, like this. We have like the time, the frequency, and the color will be like the kind of like an energy signal strength.
Of intensity of
Yes,
that
exactly.
part. Okay.
Exactly. And we use this signal strength as a color stamp, like this. It will be like generate as this.
So that's saying that for that time and for that frequency, there's a kind of strong amplitude there, right?
Yeah.
So it's telling you that, well, there is a particular frequency at a particular time that pops out.
Yes, but the thing is, the signal is so strong, when we normalize, all the quantum, all the noisy fluctuation is just go to zero. It just vanish. So we are like suppressing our noisy by doing this.
Right, in this case, but even in the previous, you could tell there was a little kind of bigger amplitude zone in the
Yes,
image, right?
yes, it was. But let me show you some data here so you can see, you can understand like I'm trying to say. So I generate this data set and I share it to you guys here. Let's open background. So, okay, this has no signal. This is only random fluctuation data. Okay, it's take a little bit of time, but hopefully we will open. And here on the right side, we have signal plus random noise. Okay, I think it's take a little bit. Not all power of the word is enough for the set of these images. Okay. Yeah, finally. So do you see here? This one is really good example. You see? This doesn't have any gravitational wave, okay? However, here, let's open. Here, we have some signal of gravitational wave, okay? For human, yeah, do you see? However, the machine can see the difference here. You see? These are really good examples. These are like trying to make the things like really useful. Because if I only give data like this, okay? If you only give data as this way in the machine, I mean, it doesn't make any point. I can do this prediction. I can say that like there is a signal here. I can do this kind of thing. Okay? So there's no point to build a machine learning model like to try and asking for fundings to buy GPUs, unless you are like my wife like to say that's like I finally found a way to funneling some money to my game addiction.
Here's frequency versus time.
First time, it was always like this. It was always like this way. And by building these kind of things, make things harder to the machine, and she can learn. I mean, she can learn like this way. So at the end of the day, what we want to generate is this kind of data sets like this. Of course, we are not the one always imposing this kind of thing, because it's kind of really hard, and the machine will not get enough information for you. But sometimes you feed this, you feed like this kind of data, which is really clear. And see here, and this is another very funny thing, because you see here, because you have like blue first, green, and the red, and you have like the time. What happens here? The gravitational wave pass in the Virgo detector, and later pass to the LIGO Livingstone, and later LIGO Hanover. It was like this, and this kind of a pattern like this, it will help the machine to not only to detect, but to localize in the position space.
Right. So just to summarize, so,
Yeah.
so what you did in the previous image is to transform stuff.
Yeah.
At the end of the day, it seems to me you've done just a Fourier transform, and then you did some amplitude analysis
Yes.
of
Yes.
modes,
Yes.
right?
Exactly.
Yes.
Exactly.
That's it.
That's it. That's all. That's all.
Very
Because we are using these images to make this. If I want to make like, I can build a model with the waveform directly. I can build this kind of thing. I only built this because it was easy for me to work with images. But we can also build this kind of directly from the waveform. So okay. Any questions?
Can I make a comment?
Yes.
On this thing? You see, Carlos, the thing I mean, it's interesting is that when we look into the picture, we can actually see, and that's my feeling about how the machine learning code actually realizes that it has a signal, because it does not deal only with the absolute amplitudes in each one of the pixels of this image, but actually it knows the gradients, because it knows that a specific profile of a signal, it can be big here, but then it has some shape. And so I have the feeling that although it becomes, in several situations, it becomes for a human very difficult to really understand the immediately because when we look into the image, what our neural network really grabs is immediately the image based on intensity. But actually what the system does is that's my feeling, is that it still can get the evolution of neighbor beams, and these neighbor beams have these fluctuations that the signals actually behave like signal-like, or in other cases like a more stochastic behavior like background, and immediately knows, well, this looks, even if it's not very clear from the intensity that you see, the fluctuations, the relative fluctuations from beam to beam actually can give still some perception about the presence of a signal or a background.
And also another thing that's like, this is not like a wishful thing for us. We can see, I mean, it is not the next lecture, the next lecture, like the other lecture. We are going to see a thing that is called the CAM, CAM, which is like a class activation map, like this, which you can give training as crazy the machine to do this classify, and say like, and open the hood of the machine and say like, okay, what is this last layer that makes this classification is seeing on the image that we have here, which make that machine predict if it is a signal or if it is a background. Want to make this, and we see these CAMs, like these class activation maps, and we see that it will concentrate it will give like heat regions where the patterns, the gravitational waves occurs, or patterns of noise, random noise occurs.
Well, let me just make a kind of additional comment to this discussion, which I think is very important. And so we are talking about signals as if it is a unified thing, but it actually isn't. So you can have different types of signals, and this is the key point. So we've been focusing on a binary coalescence. And here there is an increase in frequency of some sort, that can be a modulation, but if you have some sort of a transient, like in core collapse, it will be a different sort of signal.
Yeah.
So the telltale for machine learning will probably be different as well. And so this was the reason I was trying to inquire when the algorithm learned what the signals should be,
exactly,
you know?
exactly.
Because different sorts of signals have to be given in order for the algorithm to learn what it should be looking for.
Exactly.
So,
But the thing is, these things, as I said, like these are as dumb as you can get, and it will learn the data that you give. However, we can make, they are dumb, but they are flexible. I mean, we can like open them and say like, okay, when they are not sure if this is a signal or background or anything that you never saw before, tell me this. And we can give this option to the machine, and she always gets something that's really funny and say like, see, I have this data that I never saw before, but at least I have some confidence that has something related to the gravitational wave stuff.
It doesn't look like noise.
Yes, exactly.
Right?
Yes, it has this flexibility that we can impose. And we can also build another models with this kind of a thing. So we can give to PyCBC our approximants for this kind of a special behavior. This generate this data and look for the data from the LIGO and see here in these kind of things that are not classified as gravitational waves. And you say that's like something fishy here. It might be from this kind of exotic objects, this kind of new things. Because we generate from this data set and we have this machine learning model and the predictions can match with this thing. And it should be analyzed with a little bit more careful.
Yes, of course, the more generic it is, in the sense of checking it's not noise, the more interesting it is.
Yes.
Because we have a few models of things that we believe exist and should be there and eventually will be detected. But the most rewarding situations will likely be unpredicted possibilities. So the possibility of testing if something is not noise or if it's likely not to be noise, it's really interesting.
Yes, we can do this. We can build this.
Can I make another comment, Philip? Because the discussion is becoming very interesting.
I mean, you guys have to give some 20 minutes. This guy,
No, but I think Carlos is raising some questions which are very important. That's the reason for these meetings, is exactly to discuss this. And I mean, my feeling about this is the following: is that we have now something which is very clear in terms of we know exactly when for instance, for this case of the two black holes, we know exactly when in time these black holes merge. So there is a very clear signal there for the highest amplitude. So one of the things is that we can immediately apply these methods and know, look, we have a good signal. We know that it is there, so we can actually understand everything. But actually, to me, it looks very interesting, even the inspiral phase, to really have a dedicated program for the inspiral phase, because this means that we are moving towards a lower amplitude and also in a kind of a different frequency regime. So actually, in my mind, it makes sense that we have the highest amplitude signals, and then we have to dedicate a program for the lowest amplitude signals, which includes the inspiral phase or the echoes at the end. And once we will be there, I have these feelings that actually we'll be able to really separate individual signals from the noise itself, because the patterns, we will learn about the patterns of these signals. So I think we are grabbing still, the first steps of these, but there is one thing which is for sure necessary. In order to make sure that we can actually do the job, we would need some examples of waveforms of these events. You see, Carlos, that's the thing that would allow us, because at the moment we are fighting for the lower masses of even the black holes. We know that we will have a dedicated program there. So it's kind of an enthusiastic program, but actually it's a challenging one. But we were quite surprised that this worked even for the biggest signal. So I have this feeling that this is going to work.
Yeah. Shall we continue? More thing to add? Any question? Any question? No, so far? So far, so good? Are you still wake up? Okay. So Now is the fun part. Now it's like, okay, this is very, very technical. This is a thing that I really like. And it is, you have to build a function that wraps everything that we have done so far, but make this automatic. So we have like to create this huge function that like go load the noises, sample some rates, get the things that we have done, filter, put inject the background on the signal, make all of this automatic. Yes, you can build this function, or if you have the luxury of have like some PhD students, you can ask for them to look for tutorials and build the function for you. Or you can just go and copy and paste what people have done and go and poking around and try to do this. And this is more related to the second to later one that was like this, because this code here, this function, it was built by me and Osvaldo as well. It has lots of parts that he developed. It has some parts that I developed. It has a lot of really fun things, and it works. At least it generates what we have done. It's not the most efficient one. I'm pretty sure that has like a way better function that makes the job that we need. But it's like they always say, that's like, if it's not break it, don't try to fix it. So it's okay. But I guess that it's someone with better experience and try to do this. I'm building the same function to run on CUDA. I have like some tests and I could run the data set very fast on this. But this will run on a CPU and it is pretty good. I mean, it will take a little bit of time, depending on the size that you want to generate and how many cores and threads are available for your machine. So what this thing does at the beginning here, it is just like take some, this is some randomness that Osvaldo put here, just like when you are sampling some noise, you are not sample only from one source. You are sample always from different sources and always from different timestamps where you inputs like this. And these are really, really good. I mean, we have guaranteed that we are not using the same kind of noise again and again. Because if you are doing this, the machine will catch immediately and will be in a bad place. Okay? So, yeah, I really, really don't like this if else, but if it works, if it's not broken, don't try to fix it.
It's bad. It's bad.
Yeah. So here it's also like because we are going to sample different masses for the objects, for the two objects like this, and we can set a maximum for the masses. So in that case, I set the maximum of 50. You can set a maximum of 100, 120 black holes. Now we have like this gigantic object. We set up this, and it will always try to generate these two random masses based on the complementarity order, like this. It will be like the sum of these two masses, it always be 50. Okay? I mean, no, it always not be 50. The highest mass, the object with the more massive, it will be at the most 50. It will be like, this is like the ceiling for our object, right? So, and we have like this distance here. This is mine because what I did here is because like sometimes the gravitational wave comes from different places of the universe. I'm assuming this. And this gravitational wave will pass through one of these detectors first. And here I'm selecting randomly which one will be first. Okay, this will be my reference detector like this. This will be like my zero detector, and I will shuffle the time. I will shift the time based on this reference. So to not like select it. Thinking about even this, if I impose, if the detector will be always 1 first, always like, let's say if the detector will be always virgule, the machine will differentiate this, will catch this. And they will use this in inherent advantage to get the predictions, to get the things that are supposed to do. So even this you have to think about, okay? So here we are randomly selecting one of these 3 detectors to be our main reference, which we are going to use later to make the time shift on the series like this. And here I'm giving the inclination, like the factor for the inclination for the binary black holes, and also I'm giving some polarization and some declination, some factors here, because these are factors used by the detectors. We are imposing some detector patterns on here, and we have like to generate some random patterns before. Okay? So we have like the same get waveform time domain, and we have these 2 approximates here. You can try to change with another one approximate, or you can try to change with only one. One thing that Osvaldo noticed, it was like every time when the mass is become too low, this approximate will not work anymore. So we have like to change to another approximate. So we can do this, but most of the time it works fine. Okay. You can even set a ceiling like a minimum maximum of 4 and a maximum mass of 100 of this to not get this error like this. And here we are just doing the same thing that we did before, that we did in the cells above. We are generating the polarization, the HP waveforms. I always get confused about waveform polarization and time series. We are setting the timestamps. And here is a little bit more interesting because I'm getting the time delays between the detectors. GWPy has this very convenient function that is like time delay from detector. I mean, more directly impossible, where you give the detector reference and the position, like the right ascension and declination, and the time that was the signal arrived. And it will returns to you the time delay difference from each one of the detectors. Like this. You always get like this kind of thing. And this will be useful for us to generate the shift on the images, like the time shift on the images. And here we are just like projecting our signal here that we generate here. It needs the polarization, the H plus and the H cross waveforms, and also the position on the sky, like the right ascension, declination, and all of this. And this, we are already creating, like our signal are really putting the patterns of the detector on our signal. We are already like inject these kind of things. So this is already helping us. We are converting now in a time series, like this, for more GWPy friendly. Cropping, selecting the index, like centralize the signal that we have. We're doing this. Remember, we only did for one detector, I mean for one case, and we are going to do this for the 3 detectors at the same time. Why, you ask? Because each one of the detectors will be one of our color channels. Each one of these will be like this. We generate this image. So I not only have to think for once, we have to think for 3 detectors. But if you do for one, you are doing for the other 2 as well. Calculate the amplitude spectral decomposition to using the whitening and generate the Q graph. Doing this, and we are generating the Q graphs here. Okay, I generate the Q graph for both signal and background. Vigo, LIGO Hanover, LIGO Livingston, all of this. Same patterns, same thing, nothing funny at all. Okay. Here it became a little bit more of a computer vision stuff, more of an image stuff, because these Q graphs here, they have the range of the values are the same range of the signal strength, like the strain of like 10 to the minus 21 or something like this. And the images, as we all know, they, at least for the computer vision side, they are normalized, they are numbers between 0 and 255. Okay. Of course, if you are dealing with RGB images, if you are dealing with CYMK, I think in the range it will be like from -60 to 128. I don't remember exactly like this. But it's a bit of funny range like this. But we are going to generate RGB images. So we have like to normalize this as RGB images. Like here that we have at the end, we have like values. We have like the dot values. I asking to, instead of return like some object, like some tensor vector or something, return the matrices for these Q graphs like this. I'm getting like an image is a form as a matrix, and I can use NumPy to normalize this. Here, I'm just like normalizing for this size, like from between 0 and 255, like this. I'm doing this normalization thinking about the images. So all of my images, all of my signal strain, it will be converted in this kind of normalization. Why I'm telling this, why I'm saying this? Because this is important, because every time when I do some kind of a normalization, some kind of thing, or funny thing like this, we are losing information on this. And some of this information can be very, very important. However, we have to work with the images. We have to deal with this. So you always have to keep in mind the balance between how much information are you willing to lose to get your job done, okay? Of course, you could like use different kind of normalization, different kind of data set, and you not lose so much information at all. But since you are dealing with these images in computer vision, we have like to give up some of this information. However, so far, the information that we lose doesn't make difference for the machine. So maybe we are in the right path, okay? So this funny thing here, this normalization is just like to do this kind of a thing, like transform all my matrices, all the values in between 0 and 255, okay? And at the end of the day here, what we have, the options, we are take these matrices and you are stacking one over other. When you are stacking this, we are creating, yes? Oh, no. Voices from beyond. So when we are stacking this, we are creating a new vector which has the dimensions of the Q transform, but it has three depth. It has like the three channels: the red, the green, and blue. And we are stacking here like the red, it is Hanover. The green, it is Livingston, and the blue is vehicle. Okay. We are creating these stack images. We are create this image from array. It's a function from Pillow that generate images from NumPy arrays, and here is a NumPy array that we have. Because the plot doesn't show to you the plot like before, like this, it doesn't show to you the trick, because these matrices that we generate, they are inverted, they are flipped, they're always like this, like they're like, this is like every time NumPy does this kind of a funny thing. Every time when you generate some sort of a matrix or anything like this, it always be the transpose matrix. Don't know why, don't ask, but you all have to keep in mind. You could export this, but you always saw. Yes?
I think it's because you know, the matrix, the matrix is organized in a way, but then if you put it onto an image file,
yeah, the image
it's organized backwards. So
yes,
the way
exactly.
it wants to read it backwards.
Yes, exactly. So it has this kind of a fun indexation for the images. The index for the images starts like from the top left. I think that's something like this.
Yeah, something
and
like that.
The image from the matrix starts from the bottom the bottom left, like this. You have like to keep in mind to do this kind of flip, like this. And okay, no big deal. You just like ask this transpose, and it will do this kind of a job for you. And you do this just like, okay, flip top to bottom. Just pass this, and at later, because you can generate, I mean, it's a very good exercise. You can generate some few images, like 20 images, without pass this resize, and you see, and you remember me, then I say like, okay, we have like these wide images, and it has like not matching dimensions, like this. And later I'll have to deal with this in the machine learning stuff. However, because I'm lazy, I'm slack, I always put like, okay, take this image and resize it on this. Also, when I'm doing this, we are also losing information like this, because we are losing a lot of time information, especially. And depending on the way that we compress on this, you start to see some different artifacts. Right? One thing that I want to test, once we finish the workshop and we finally publish the paper that we worked, it is to use a nicer way to compress images, like to only throw away things that really don't matter for the image at all, which is semi-cut. That's the name. And I've been testing this with Jetty images, and it has been working very well. And I'm really excited to try this on the gravitational waves, because this final step here, this thing here, this hurts a lot on my information side, like this. However, as I said, like one might have to finish his thesis and defend his PhD or master degree. Okay. All of these funny things here is just the format file from Python. Size Python 3.7 or 3.6, I don't remember what it was like. You can pass this F over, what is the name? It's not quotation mark. What is like this single quotation marks like this? Once you pass this F and these brackets, you are passing like a format file like this. What you're saying is like, okay, we'll save this image with this name, and in this space, like this, you have this path, you will fill with the things that I want, just like this. So you don't need like to fill every time an image or anything like this. And this is just like filling these names, filling all of this for yourself. This is, I mean, this is really useful for you, especially if I generate lots of images, lots of files, lots of things. And as I said before, this Frankenstein here, this Frankenstein, it is pretty much summarizing this in this image like this. Okay, we have like codes from me, codes from Osvaldo, codes from lectures, codes from things, but it's working. Okay, and you can always take on, improve it, and generate your data set. To generate the data set, you just, okay, I'm having 12 threads available. I'm using multi-threading on Python. It's really easy to use. You just take this and use this function like this pool IMAP, unordered. Give the function that we create. You always have like to create a function, and it will take the function, take the things that need to do, split in all my cores, in all my threads like this, and make the job. It runs faster, it runs a little bit faster. If I try to run, you can run this on the Colab as well, but unfortunately, Colab will only give you 2 threads, unless you pay for Google for this. Or you can give run on your machine and give all the threads that you want, or at least me, I like to not fill the pool of threads, just like give some 8 threads. It will generate, I mean, in this case, it generates for me 5,000 images in something like 7 minutes, 8.5 minutes, or something like this. Okay. I'll not generate 5,000 images again because I already have here, and I don't want to erase my images like this. But that's it. If you want to generate a little bit less, you can just like take this and generate 500 images, or you can 50 images. So this underscore here is really good for me because before I always get confused with how many zeros, and I always get like, okay, this. And here I know that is 1,000. So if I want like 50,000 or something like this, I have like more control on this. And I think that's all for today. I hope that people will try to learn. And if I received some email of people that were not able to download the data set, please send it to my email, and I can share you the link, and you can download the data set, so you don't have to run this. But ideally, I wish for the curious people ones, for the ones that they really like it, try to play with this. Try to play with this kind of thing. Okay.
Okay. Thank you, Alec, for another nice lecture. So, are there questions? More discussions?
Oh, by the way, tomorrow we generate the data. Tomorrow we finally get to the machine learning with gravitational waves. Okay, it's not a promise. Tomorrow it is the lecture for tomorrow. So
Tomorrow
yeah,
is the lecture.
tomorrow will be finally we will make something useful. Okay.
I think it was already useful.
Okay.
So I don't know if anybody wants to say something. If not,
Yeah.
let's just thank Philip and all the other lecturers today. And so maybe we can thank.
Okay.
And we meet again tomorrow at 9. And that's it.
I think it was a little bit harsh this lecture because it has lots of codes and things that are really messy for me. But don't be afraid. I mean, try. The worst thing that you can have, you get a really nasty error or some loud noise from your machine, but it will not explode. I promise. Okay.
Yeah, that's good.
Yeah. Okay, very good. Yes, by the way, if you could not download the data, send an email to me. It has on the page, or just ask to Antonio Nofri or anyone, ask for me, and I can share the link with the data set. Okay. That's it.
Okay, so
Okay.
let's close it and see you all tomorrow. And hope you have enjoyed and also found today's lectures useful. Okay, see you tomorrow.
Okay, Antonio.
Bye-bye.
Bye.
Very much. Bye-bye.
Bye.